To continue our discussion of phases and ways of charting phases, the next type of diagram we can look at are phase diagrams. Now, a phase diagram essentially provides a map of phase in relation to temperature and pressure. It's going to look different for every substance, but we're going to have common features. These features are going to include regions. We're going to have regions for solid, liquid, and gas that indicate temperatures and pressures at which each phase is stable. So we have here the example of a phase diagram for water. So we can see our regions for solids. We've got that orange block. We've got this green region for liquid, and we've got this blue region for gas. Then we're going to see lines. So the lines are going to be labeled in black, which are separating the regions. These indicate temperatures and pressures at which we have an equilibrium between the two phases. So with our heating and cooling curves, when we got those plateaus, we had a mixture of solids and liquids or liquids and gases. We're going to see the same thing here. We're going to get a mixture of the two phases present. Now, a change in temperature or pressure that results in crossing that line will lead to a phase change. So we've got that line between solid and liquid. If we're sitting on that line, we have solid and liquid present at that temperature and pressure. If we're on the line between liquid and gas, we've got liquid and gas present. If we're on the line between solid and gas, we have solid and gas present. So other features we're going to see on our phase diagrams are going to include a triple point. This is the temperature and pressure at which all three phases exist. So this is going to be where our three lines meet. So right here, we have our triple point where all three of our lines meet. We also encounter a critical point. This is a temperature and pressure above which our substance becomes a supercritical fluid. This is another phase. So we've got solid, liquid, and gas. That's our common phases. Those are not our only phases. They're just the ones we encounter most commonly. So a critical point or supercritical fluid is a phase in which we've got a substance that is got properties in between that of gas and a liquid, and it kind of shares properties of both. And that occurs at very high temperatures and pressures. So that will always occur at the end of our line separating our gas and our liquid. So on our diagram here, this is our critical point. So any temperature or pressure above that point, we have a supercritical fluid. Another important feature is the slope of the solid-liquid line, known as our fusion line. That line is going to give us an indication of the density of our solid compared to that of our liquid. Now, this phase diagram is the phase diagram for water. Notice that the slope is negative, so it's leaning back towards our y-axis. So we got that negative slope. This is actually unusual. The negative slope is indicating that our liquid phase is more dense than the solid phase. Again, that's rare. More commonly, your solid phase is more dense. Water has this feature because of its lovely intermolecular forces. It's hydrogen bonding. Most substances, though, are going to have a positive fusion slope. So one of the things we need to be able to do with our phase diagrams in this chapter is identify those important features. Identify where we've got solid, liquid, or gas, or mixtures. Determine what that fusion slope means. Where's our critical point? Where's our supercritical fluid? So if we were to have a positive fusion slope, we just said the negative fusion slope means that the liquid is more dense than the solid. If we were to have a positive fusion slope, it means that the solid is more dense. So we've got the following phase diagram, and we're asked to identify the phases at each point. So anytime we look at a phase diagram, again, the sizes of the regions will be different, the slopes of the lines will be different, but we're going to find them in the same general vicinities. So that first thing we'll always encounter, that upper block will always, where A is, will always be solid. B region will always be liquid. C region will always be gas. Now D. So D is occurring up above that solid liquid line. So when we're up there, that is our supercritical fluid. Now, if we look at E, we're sitting on the line that separates solid and liquid. So that means at E, we have solid and liquid present. F is between liquid and gas, so we have liquid and gas present. G is the intersection of all three lines, so we've got solid, liquid, and gas present. So now we're given another phase diagram. We're asked to identify our triple point. So the triple point is going to be a temperature and pressure. That is going to be where those three lines meet. So if we look at this phase diagram, the corresponding pressure is 0.5 atmospheres. The corresponding temperature is 10 degrees Celsius. So my triple point occurs at a pressure of 0.5 atmospheres, a temperature of negative 10 degrees Celsius. And if I'm at that temperature and pressure, then I have all three matters or phases of matter existing at the same time. Now we said our phase diagrams would be useful in identifying phase changes or what phases we would have present at a given temperature or pressure. So here we're asked what phase change, if any, would occur if our temperature was changed from negative 15 degrees to 100 degrees at a pressure of 0.5 atmospheres. So we're right here at 0.5 atmospheres. We're going from a temperature of negative 15 to say 100. So this is just going to be an estimate. So what we've done is at negative 15 and 0.5, here we're in that solid region. We increased the temperature. We kept the pressure constant. We increased the temperature. We crossed through the lines and entered the gas phase. So we've gone from solid to gas at that temperature or at that pressure. So that means sublimation would occur. Then we're asked what phase change, if any, would occur if our pressure changed from 1 atmosphere to 0.5 atmospheres at 0 Celsius. So we'll say zeros around in here. And we're going from 1 atmosphere to 0.5 atmospheres. We start off in the liquid phase. We cross the line into the gas phase. So we've got vaporization occurring. So again, with our phase diagrams, we need to identify where we have solid, liquid, or gas. Where's our critical point? Where's our triple point? If we're given a particular temperature and pressure, we need to identify what phase we're in. And if we change a temperature or pressure, we need to identify what phase change occurs. Finally, we need to use that fusion line. So here we've got our fusion line. We like to see is the slope positive or negative, and that is a negative slope. So if I have a negative slope, we're being asked, is the solid phase more or less dense than the liquid phase? If the slope is negative, the solid is less dense. It's the liquid that's more dense if that is negative. So we've taken a look for pure substances. So here with our heating curves, for right now, you can also look at mixtures. And you're going to see in lab comparing a pure substance to a mixture in terms of a heating or cooling curve. Phase diagrams. We're very often looking at pure substances and charting how our phase changes with temperature or pressure. Next, we're going to get into talking about mixtures and looking at solutions and how our intermolecular forces are going to impact solution formation.